Hi there. Welcome back to Weather Analysis with Mr. CB. And I decided to make a video just kind of reviewing everything that was in those lectures. Um, this course is divided into two parts. And so this is going to be a review of everything from the first 14 lectures. So this isn't necessarily the most formal, um, whatever you would say, type of review, but this is going to be kind of a long video, I'm just going to say, but it's important to go through this stuff. It was kind of a lot of content, so I felt like it might be nice to have it concise. I will say I won't have such detail when I'm going over this because I'm not going to just repeat everything exactly that was in those videos. If you want more detail, just watch those videos. Um, so also, as you can see up here, some easy things are omitted. So like things that might be considered pretty straightforward might be omitted. So it's really going to just be the bulk of the more complicated stuff, I guess you'd say. But it should cover basically everything that I had in those videos. Um, Now the first thing I want to say, just as a starter, is just remembering that winds are always given for where they come from. Okay. So if you're told that there's a westerly wind, that means it's coming from the west, going to the east. If you see a station plot that has the flag pointing to the left, I don't know if this is mirrored, so sorry, but to the left, that means it's coming from the west. Once again, it's always where it's coming from. And the reason why is because we want to know what environment that's going to be brought to where we are. That's the whole thing. What do we care about what's away or like further ahead? Like what do we care? Like we want to know what's coming. What's coming, you know? That's the whole thing about, meteorology, okay? All right. So, let's zoom this thing in a little bit and we're just going to go through these and they're not exactly organized in a particular way, but we'll just go through these. Okay? So, all right, let's get started, all right? I think there's kind of a lot of things on this, right? 161 or 173. Oh, 176. Oh, okay. Let's just yeah. 189. Okay. I made this thing, so shouldn't I know how long it is? But all right, sorry. Let's start at 1, okay? Make this thing on 2x speed. How about that? All right. Environmental lapse rate is what? Approximately, I'll just type it, okay? 6.5 degrees Celsius per kilometer, not constant, okay? And that's given by the red line on the Schutte log mean. We'll talk about that later. But it's going to be about 6.5 typically. What is the cause of wind? Some of these I'm not going to type it, okay? I'm just going to say it because that will take too long. All right. The cause of wind is that there's a horizontal difference in pressure that goes from high to low. So high, low. And if you have closer together pressure differences, um, meaning more closer pressure lines, isobars, then faster winds because it goes through those quicker. They're spread apart, slower wind. What is a lapse rate? A lapse rate is a change in temperature with height. And that is temperature decreases with height until you get to the inversion, remember? All right. Warm air above cool air is stable because warm air rises, cool air sinks. So they'll separate and just be like, eh. Cool air above warm air is unable. How about unstable? Okay. And I have these wacky gloves on because I'm in my car and it's 9 degrees outside. Okay. Not that good. Um, what is an inversion, number 4 or 5? An inversion is number 4 because if you have warm air above cool air, that's not typical because, like I said, it usually decreases with height. But since that happens, it's inversion. What is latent heat? Latent heat is heat that is a result of a phase change. Okay, that's what that is. What is evaporation? Is it a heating or cooling process? All right. Evaporation is where we go from a liquid to a gas. Is it a heating or cooling process? Here's where it can get confusing. It's a cooling process. Doesn't that sound like it's a warming process because it goes from a liquid to a gas? But remember, we care about um basically if let's just say a molecule is going from a liquid to a gas, um, energy is not created or destroyed. So because the parcel itself is increasing in temperature, it decreases the environment around its temperature. So it's a cooling process. So that's the thing about this stuff. Sometimes there's things like that that are just counterintuitive, but you just gotta be careful. The parcel itself might be warming, but it to do that, it has to cool the surrounding environment because if one thing goes up, the other must go down to maintain balance. Okay. Right. Melting. Melting is going from a solid to a liquid. And once again, that sounds like it is warm. The parcel's getting warmer, but it's cooling the surrounding environment. So it's a cooling process. Freezing is, of course, going from a liquid to a solid. It's actually a warming process. The parcel is cooling, so it warms the surrounding environment. Sublimate, or I skipped one, sorry. Condensation is going from a gas to a liquid. And that is a warming process because the parcel itself is decreasing in temperature, yet it is warming its environment. Sublimation is going from a solid to a gas. Um, and so once again, if you ever hear someone say snowflakes are melting, actually they're sublimating because it's going from solid to a gas. And that is a cooling process because the temperature of the parcel is decreasing, so it warms its surrounding environment. Deposition is going from a gas to a solid, and since the temperature is decreasing of the parcel, it warms its surrounding environment. So as a review, the MES, melting, evaporation, and sublimation are cooling processes, and the other three, which are FCD, freezing, condensation, deposition, are the warming processes. What is sensible heat? Heat that we can feel and measure by the touch. What is convection? It is vertical heat or energy transfer. What is advection? Horizontal um, heat or energy transfer. What is mixing ratio? It is the ratio of water vapor or the mass of water vapor to the mass of dry air. What is the saturation mixing ratio? The mass of water vapor to the mass of saturated air. So you calculate that as mixing ratio, mass of water vapor divided by mass of dry air. Saturation mixing ratio calculated as mass of water vapor divided by mass of saturated air. Okay, as temperature increases, the mixing ratio does what? Increases. What is vapor pressure represented by the variable E? It is pressure that is exerted by water vapor. What is the saturation vapor pressure? E sub S, the maximum vapor pressure based on the temperature. As temperature increases, the vapor pressure increases. So let me just put that, okay? I'm not typing some of the things, but I'll at least put that. Relative humidity can be measured as this ratio or this times 100. And what it is the amount of water vapor there is compared to how much the air can hold. And then, so if it's 100%, then that means that there is the maximum amount of vapor pressure or water vapor that the air can hold if it's 100%. Almost think of it like as a percentage full of water vapor. So next we have the dew point temperature. The dew point temperature is the temperature that the air must cool for saturation. So if it's the same as the actual temperature, if they're equal to each other, dew point and actual temperature, then that means that the air is saturated. It doesn't have to uh, go down at all for there to be saturation. It already is saturated. What is wet bulb temperature? It is the temperature air would be if it was cooled adiabatically. Um, and through evaporation. And then also is basically a measure of moisture in the air. Dew point depression is the difference between air temperature and dew point. As height increases, density decreases. What is the pressure gradient force? It is the force that causes wind to move from high to low pressure or even high to low height. What is the Coriolis force? It is the force that deflects winds to the right in the northern hemisphere due to the rotation of the Earth. Um, as wind speed increases, so will the Coriolis force. As latitude increases, so will the Coriolis force. So as you go away from the equator, geostrophic balance is if um, the pressure gradient force equals the Coriolis force. Um, and that would cause wind to go flow parallel to isobars or isoheights. Now, if there is friction in play, at play, such as near the surface, that is going to mean that there's ageostrophic flow, and it's not exactly balanced, so it's ageostrophic. If you remember my cheesy video. The centrifugal force can come into play, which is a force that points towards the outside of a curve, um, which is going to cause some deflection. Talk more about that later. All right, now we're moving on to divergence and convergence. Divergence is going to be fast winds ahead of slow winds. I don't really need to type it honestly, but um, it, so remember, if you let's just pretend there's like this speeding sun that leaves the ground level behind, there's divergence, a gap created, and in the upper level, air is going to rise to fill that gap. Sorry, just knocked something down. Um, and in the lower levels, since air can't rise from below because you're at the ground, it's going to sink from above to fill that gap. So that's what these two statements are meaning. Like what's going to happen when the gap is created. In the upper levels, air will rise from below. In the lower levels, it will sink from above. Convergence is going to be slow winds ahead of fast winds. So it's converging like the grandma, slow grandma in front of the speeding person behind. In the upper level, air is going to sink when that happens, and in the lower levels, it's going to rise. Diffluence is just basically divergence that occurs like directionally, like it's spreading out, wind is spreading out. Confluence is it's coming together, and the same things exist these A and B points for those situations. Um, so before a trough, are we going to have convergence or divergence? We're going to have convergence. After a trough, we'll have divergence. So because we have divergence after the trough, that is going to be just after the trough is where we'll have air rise from below, if we're talking about in the upper level. All right. Now, moving on to section 2. What is radiosonde? Radiosonde is something that's attached to weather balloons, that's going to give us our station data. SCU-T log P use, that's basically what's presented on that is from the radiosonde. And that's going to help us know how things are changing as we go up. We'll talk more about that later. Reading a SCU-T log P, we're actually going to look at later. Stable atmosphere, I already said this earlier, but if we have warm air above cool air, I don't know why the answer is already on there. Sorry. Um, unstable atmosphere is cool air above warm. Neutral atmosphere is going to be similar throughout. All right. What is the environmental lapse rate? We actually said that at the beginning. It's approximately 6.5 degrees Celsius per kilometer. But it is basically how is the environment. Remember, the lapse rate is how temperature changes with height. The environmental lapse rate is saying, what is the environment doing as we go up? and that is measured by the radiosonde and is presented as the red line on the Scuti-LP. Now, the other lapse rates that we have are the dry adiabatic lapse rate and wet adiabatic lapse rate. And once again, the answer is on there for some reason. Um, it looks like for the next few, it's actually on there, but sorry about that. But anyways, still, the dry adiabatic lapse rate is how both of these are how a parcel would change as we go up. What would we expect a parcel do as it goes up? Um, and based on this is how we determine certain things like CAPE or SIN, which will be important. Now, the dry adiabatic collapse rate is how the parcel would change, how its temperature would change if the air was non-saturated. And that's always going to be about 10 degrees Celsius per kilometer. Um, And then the wet adiabatic lapse rate is how would the parcel change with height if it's saturated? And it's typically, it ranges from 4 to 7 degrees Celsius per kilometer, but we can just use 6 sometimes. Now we can determine if there's stability or instability based on um, the order of these lapse rates. So if it goes that the basically the parcel lapse rates are greater than environment, um, which would mean that the parcel is cooler than its environment. That sounds backwards, so you got to be careful about that. But it's once again the thing being that comparing the parcel itself to its environment. But it's cooler than its environment if this is the case. Because if the think about it like this, if the lapse rates are greater, then it's cooling quicker. So that's how it's cooler than its environment. So if the lapse rates of the parcel, the D and W, are greater than the environment, the parcel's cooler than its environment, which means absolute stability. Because if it's cooler than its environment, it sinks. Absolute instability is if instead the lapse rates of the parcel are lower than the environment, which would mean that they're cooling less quickly than the environment, which means they're going to be warmer than the environment, which means that they'll rise, which means it's unstable. Conditional stability is if either lapse rate of the parcel is on either side of the environment, which means, ooh, sometimes. Which, as you can see in this case, for the dry adiabat, stable, wet, unstable. Um, and that's what I just said. Saturated parcel is slower than its really wet. The wet parcel is slower than its environment, which means unstable because it ends up being warmer. Saturated parcel, unsaturated, the dry adiabat, faster rate, which means it's going to end up being cooler than the environment. It will sink and stable. So that's why it's conditionally stable. Sometimes it is, sometimes it isn't. Parcel trace, we'll talk more about later, and the mountain trace. All right, now let's talk about these freaking things. Um, wait, actually, oh wait, no. I realize that these are listed twice, but it's different ways of saying the same thing. You'll see what I mean later, but I'll still say it now. So the LCL is the height where the air is saturated if a parcel is lifted adiabatically. So it's the height at which the parcel becomes saturated, where saturation occurs, basically, where the cloud base will be. Um, LFC is the height where the air becomes warmer than its surroundings. Sorry, the parcel becomes warmer than its surroundings and will start to rise. The equilibrium level is what EL means, and it's the height where the uh parcel is again equals the temperature of the environment. And then that's the top of the thunderstorm. So eventually the parcel will be cooler than its environment, and then no longer can it rise anymore, which is why that's the top of the thunderstorms. So that's what the EL is, where they equal each other, and then above the EL, then the parcel's lower than its environment, cooler in its environment, which means it sinks only to the equilibrium level, which is why the top of the thunderstorm say. CAPE, remember, is convective available potential energy, and it is the shape that's created by in between the LFC and the EL. Um, and that is the more that is, the more basically the higher percentage of thunderstorms or higher chance, sorry. And then SIN, CIN, sorry. Oof. It is the shape that's below the CAPE shape, and it's the energy that's able to lift the parcel to its LFC, which is the point where the CAPE starts. CCL is the height where the parcel is going to rise adiabatically to saturation. The CT is the surface temperature needed to start convective clouds. And the cause of the CT is solar heating. Be able to identify the features on SQT. We'll do that a little bit later. All right. So now we will see what we have here. So for an upper level plot, what are the different things? So this, once again, would mean that the wind is coming from the north. And then this right here, to the top left, is going to be temperature given in degrees Celsius, important. Um, this 2 is dew point depression, not dew point depression. This 3 is a geocoded height, which is going to be 3 numbers, which um, you will add a 0 to the end. It's in decameters, but to get into just meters, you add a 0 to the end, sometimes even a 1 to the front. If the number, let's say it was 030, obviously it's not 300 feet. So you you need to add a 1 at the beginning. So that would be 10300, 10,300 feet. Um, the 4 is PP. We actually didn't really talk about it. So really 1, 2, and 3 things to know. 67. All right. Oh, I already said that. How to decode the thing. All right. So 300 millibar level. What meter heights is that approximately at? Not everywhere, because once again, the 300 millibar map is going to have that pressure everywhere, but differing heights. So it's going to be about 10 to 13,000 meters is what the level of this is going to be. What is identified at this 300 millibar level? At the 300 millibar level, we can see long wave patterns, blocking patterns, jet stream and jet streaks, upper level lows. Um, that's kind of the stuff. The level of non-divergence is at approximately 550 millibars. Or sorry, actually just 500. All right, now these 4 right here are important. The left entry of the jet streak is there convergence or divergence? There's convergence. The right entry, divergence. The left exit, divergence. The right exit, convergence. Those are important to know. In a jet streak, do isobars tilt up or down to warmer air? They are going to tilt up to warmer air. And they're going to tilt down to cooler air. What is the cause of the jet stream? It is basically the change in geostrophic winds with height. Because differing heights, there's the geostrophic winds, they change with height, and that's what causes our jet stream. What is a jet streak with a K? It's a place within the jet stream that is localized area of faster winds, which we usually display as like an oval. And we can separate it into 4, and that's what we were talking about with the left and right entries and exits. Um, to the left of the flow is the low. So where your lower heights are is going to be to the left of the low. And careful, that doesn't usually mean like left, like west. It's really usually north, because the trough's usually like that. Um, Therefore, the parcel is going to move to the left or right of the jet streak as it goes and then moves back. So actually, it's going to move to the left because it's going to move towards the low. The forces, remember, they get out of balance. Pressure gradient force gets stronger, and then Coriolis eventually balances out with it, but then it weakens again as it exits, and then back to normal. Um, Relative vorticity includes what two? We have curvature, and shear that cause relative vorticity. As curvature increases, relative vorticity also increases. Shear means that the strongest winds are going to be in the center or the outside of the flow. Um, yeah, what? Center. Yes, the strongest winds are going to be in the very center of that jet streak, slightly weaker outside. And so you imagine those pinwheels. So above the fastest winds, it's going to be counterclockwise. Let me try to draw that just to be clear. So it's the faster winds in the middle of the thing. So if you had like, let's say a pinwheel here, what way is it going to spin? Well, it's like it gets like moved up like that, and that's counterclockwise. And then down here, opposites clockwise. Um, well, don't want that on there anymore. Okay. So number 84 and 85, these are going to be important. So there's basically five things that you need to just group together for both of these. So positive vorticity. Does that mean counterclockwise or clockwise? It means counterclockwise. Counterclockwise is positive. Is it going to be anticyclonic or cyclonic? Cyclonic. Is that associated with the trough or ridge? Trough. Is there going to be rising or sinking here? Rising. Negative vorticity, therefore, is clockwise. It's anticyclonic. It's associated with the ridge, and it's associated with sinking. Those are just five things you need to group together. To the left of the jet streak, is there positive or negative vorticity? Well, since we know that it's counterclockwise, then it's positive. Is it going to be colder or warmer air? It's going to be colder. To the right of the jet streak, negative or positive? Negative since it's anticyclonic, or clockwise, whichever you'd say. And then warmer air is going to exist. The left entrance, does it have negative or positive vorticity advection? Left entrance, negative. Negative vorticity advection. Right entrance, positive. Left exit, positive. Right exit, negative. The good thing about these is that you can pretty much, like, if you remember one of the four, you can remember the others because it's like opposite, like, you know what I mean? It's almost like cross. Um, but remember about the vorticity advection. If it's positive, we're saying that we're about to have higher vorticity advected to that. If it's negative, it was just there. So that makes sense of why that negative is at the left entrance because the fast winds were just there, but now they're not. And at the left exit, it's positive because they're about to go there. And why left? Because remember, that's the way it will move slightly to the left. The parcel will move to that area, as I said earlier. Um, Actually, this wasn't even talked about in the videos, but I'll still say this. So for the entry, is there going to be direct or indirect circulation? Um, it's going to be direct circulation. And warm air, in this case, rises and cold air sinks, as we usually expect. But if it's in the exit, it's indirect and it's opposite of what it usually is. So sink, warm, cold air rises. Misc miscellaneous of this topics that we've just done. Um, as dew point depression increases, wet bulb temperature is going to increase, but it's still going to be lower than the temperature. It always is. It cannot be higher, just like dew point cannot be higher. Heat source for the troposphere is the Earth. You might think it's the sun, but it's actually the Earth because it's originally from the sun technically, but then it's bouncing off of the earth. So gotta be careful about that. Saturation mixing ratio on a SKU-T represents constant what? Water vapor capacity. We'll talk more about that later, actually. If parcels are forced to the LCL, what can happen? Clouds can form because that's the cloud base, because that's where saturation occurs. Jet streaks are advected upstream or downstream. They're advected upstream. So upstream means further down. So that makes sense. The jet streaks are going to move further down in the flow. Low pressure system at the surface will form east or west of the trough axis, which it's not listed on here, but positively tilted is if it's like a positive slope. If you were to draw like a line directly through the bottom of the ridge, does it look like a positive slope, just straight up, or a negative slope? Um, and that's the trough axis. But the low pressure is always to the right or east of the trough axis. It's not going to be exactly at the trough. It's going to be further from it. And the higher you go up in the atmosphere, the more further. Um, jet stream flows, or the jet stream forms due to a temperature gradient or a pressure gradient. Due to a temperature gradient. The difference between dew point temperature and relative humidity. Which is a better feel for moisture and why? So for these next questions, I wrote down a cohesive statement. So I'm just going to read that. So dew point temperature is the temperature that the air must cool for saturation. Remember? Relative humidity, on the other hand, is a percentage which represents the percent of the air that's occupied by water vapor. Remember, if it's 100%, completely saturated. Dew point temperature is the better indicator of atmospheric moisture because it gives you the idea of the specific temperature that you are at and where you would need to get to for saturation to occur. Whereas relative humidity is relative, that's why it's called that, to the amount of water vapor that the air can hold. So, in other words, basically, you can have a relative humidity of 100% and it does not feel humid outside. Um, and it's because that can happen in a cold situation. Um, like let's say right now, I had mentioned earlier that it's 9 degrees. Let's just say that it was snowing. Then the dew point would be, let's say the dew point was 9 degrees. So that means relative humidity is 100%. Does it feel humid? Uh-uh. That's why dew point temperature is a better indicator. Um, because, you can actually know, oh, well, it's only 9 degrees, you know, it, you know, so that's why. All right, next, why will a parcel move to lower heights in the jet stream? Remember, I said why is it going to move high up? I say up, really northward typically, but really left in the jet streak that is like this, so it's really north. Why does it do that? Because there is a tighter gradient of heights in that jet streak, and the pressure gradient force increases because of that. And now there is ageostrophic flow that pressure gradient force is greater than the Coriolis, so that's what causes it to move. Since the pressure gradient force points towards the lower heights, the parcel will move to the lower heights because it always goes from high to low. Next, why are winds slower at the base of the trough? Why? Because winds winds are typically slower at the base of the trough because there is convergence before the trough. Remember, convergence before, divergence after. Um, for convergence, there are slower winds ahead of faster winds. After the trough, there's divergence and there's faster winds ahead of slower winds. Due to the places of convergence and divergence, the slower winds end up being at the place in between the convergence and divergence, which is where the trough is. Also, the centrifugal force opposes the pressure gradient force at the trough. Since it points to the outside of the curve, it is with Coriolis force, um, and the pressure gradient force points upwards. And because um, the centrifugal force is opposite of pressure gradient force, that also slows it down. Next, how does the upper level divergence lead to surface low pressure? Why does divergence in the upper levels mean that there will be lower pressure below? It's because, well, if there is upper level divergence, there's faster winds ahead of slower winds. This causes a gap. And remember, air rises to fill that gap. If the air rises, the density at the surface decreases. And when density decreases, pressure increases. So bingo, okay? All right, next, this is the mountain trace. The mountain trace. Um, Calculate the temperature and dew point for a parcel that is forced to rise up the windward side of the mountain and sink down the leeward side of the mountain. Um, this is considered the windward side. This is the leeward side. Because winds are usually moving this way, and there's going to be a wetter side and a drier side. That you don't really need to know that though. But a parcel, I didn't type this, sorry, has a starting temperature of 25 degrees Celsius and a starting dew point of 5 degrees Celsius. The dry adiabatic lapse rate is 10, as we expect, and it wants us to use a wet adiabatic lapse rate of 6. Assume the dew point is the same, uh, changes at the same rate once saturation occurs. Also determine the LCL. So basically we need to know what are the final things, and all right. So let me zoom this thing in. Oh, I need to go back on the normal mouse to do that. Okay. So this is not going to be very fun for me to write. I'm just going to say because I don't write well on a screen. But essentially, um, we know that why well, let me scroll up. It says assume the dew point temperature changes at the same rate as the temperature once saturation goes. So essentially, this temperature, this dew point, is going to still be 5 until saturation occurs. Then it will start decreasing too. That's what that means. So 25 degrees Celsius, 5. So since those are not equal, we're doing the Dalar, the DALR, dry adiabatic lapse rate, which is 10 um, degrees Celsius. So that it's going to be 15 and 5. Sorry, I'm not using my units, but I don't care about it right now. Okay. So now, okay, 15, 5. Oh, bingo. 5, 5. And since those are the same, this is where the LCL is at 2 kilometers. Now they're the same. Now, haha, now this dew point gets to start decreasing too. And they get to decrease by 6. Remember, that's the Waller, WALR. Now that's saturated, we switch to that rate. So not -1, -1. Now -7, -7. Now -13, -13. Oh, great. Now it starts increasing again. Well, the dew point is like, too bad. I'm just going to keep doing what I'm doing. So it stays at 13. So I already know that's what this is going to be. Final dew point temperatures, 13 degrees Celsius. Sorry, negative 13 degrees Celsius. So that thing stays the same. Once it starts decreasing, it's like, I don't care. I just will stay at that. But the normal temperature, just T, is going to start increasing again. And by what rate? It's going to, you'll see first, the Waller. So back to 7, but it's 13. Then -1, 13. Um, then plus 6 again. Oh, wait, shoot. Sorry. Wrong, wrong, wrong. It increases by the dry adiabatic rate. Right. Dry adiabatic lapse rate, always. Sorry. So -3, -3. Then plus 10 is 7 degrees positive. So remember, see what I just did, okay? When it goes down and it starts increasing, it's always by dry adiabatic lapse rate. Sorry about that. So now it's going to be 17, -13. Then it's going to be 27, -13. And then finally, the final temperature is 37 degrees Celsius positive. So bingo, that's how you do the mountain trace. Okay. Sorry for that mess up. I'm kind of stupid sometimes. All right. Oh, stop. Stop. This thing going crazy. All right. Now back to the other stuff. All right. Skew stuff. So I don't actually have a picture of a skew on there. So if you really want to see that, then please go back to that episode or video. This isn't a TV show. Okay. I'm getting a little distracted. Okay. Back on track. Skew. Let's read some of these things and figure out which one of the different acronym freaking things it's talking about. All right. The level above the LFC, which temperature of a rising air parcel equals the temperature in the environment. That sounds like EL. That's the equilibrium level. I already mentioned that earlier. The height at which a parcel, when lifted, becomes warmer than its surrounding and then is buoyant, which means it can rise. That's the LFC. Height at which a parcel becomes saturated. Oh, we know that. LCL. Area enclosed by the environmental temperature in the parcel. Da, 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 da. We know that's the CAPE. Amount of energy required to lift the parcel to the LFC is the CCL. Height at which the parcel, if heated sufficiently from below, will rise until it's just saturated. Um, oh, this is the CCL. So sorry, the other thing is wrong. The amount of energy, I should have known that. It's not a level, it's the energy. So energy that could only be K per sin. This is sin. Sorry about that. Surface temperature that must be reached. I mean, the only thing that we could have is CT. But to start the formation of convective clouds, the height of the top of thunderstorm tops is LEL, equilibrium level. The amount of buoyant energy available, that should already make you know it's CAPE. Ah, sorry. I was typing on. Area enclosed. That's sin. Sorry that I'm not reading the whole thing, but that I kind of already said this before. All right, moving on. The 500 millibar level is at about what meters? 6,000. You need to know that. I say about because remember, it's not, of course, this is not a place with equal height. It's varying height. What things can you see at this level? This is where we see positive or negative vorticity advection, some short waves. That's really what it is. Not really three things, but all right. What is a deepening trough? It is if the jet streak is before the trough. Filling trough, it's after. And for the deepening trough, we have cold air advection below. For the filling trough, we have warm air advection below. Intensifying ridge, we have the jet streak before the ridge. It's about to intensify, and we have warm air advection below. Sorry. Sometimes if I push too many keys at once, it beeps. It sounds terrible. You probably didn't hear it though. All right, weakening ridge after. Weakening ridge means that the jet streak is after it. CAA below. Zonal flow, that's east to west flow. Meridional flow, north to south. Zonal flow um occurs near the rear for which of these four? For if it's filling or filling trough or a weakening ridge. As a parcel enters its vorticity field, a place where it's higher vorticity, what two things happen? Remember, it converges verti horizontally, stretches vertically. So remember, it's like arms out like you're a skater, but then you bring it in and you're like, ooh, okay. Or you can just think of other analogies that might not be as weather appropriate, if that helps you remember it. Um, for number 114, speed will increase, then decrease. Ugh. Let me turn on my heat in my car. It's kind of cold. Ugh. Just like usual, also, it's very late. It's 12:35 a.m. So sorry that I'm tired. We're only on 116. We'll get through this, okay? Keep going, keep going. Positive vorticity advection is also considered cyclonic vorticity advection. Remember, positive and cyclonic go hand in hand. Will that be high or low vorticity advected into places where it was high or low? This means it is high vorticity advected into where it used to be low. The opposite is true for that. Low and where it used to be high. Short waves are in areas of lower or higher heights. In areas where there were lower heights. Does this mean there will be lower or higher temperatures? Lower. Will there be upward or downward motion ahead of it? Upward. Is it associated with cyclonic or anticyclonic flow? Cyclonic flow. Next, one level down, 700 millibar level. What what meter is that at? About 3,000. What things can you see at this level? You can see your upward vertical velocities. Remember the freaking omega, okay? You can see short waves also here, and you can see inversion where there could be inversions, and you can do convective forecasting. Overcast conditions are found, this is just a general fact, at relative humidity 90% plus or dew point of 5 degrees Celsius or less. All right, negative omega, what things are associated with in positive omega? I know that's a W, but I just hate Greek letters and I didn't feel like typing it. Um, Negative omega, negative vertical velocity. What does that mean? Rising or sinking air? Rise. Oh, I'm trying to control B. Okay. Vertical or that. Will we have warm air advection or cold air advection above? Below, sorry. Because remember, at the 850 level is where we have that CAA, WAA. We'll talk about that in a second. See, right here. And then above at the 300 level, 500 level, PVA or NVA. Dun, 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 dun. Positive vorticity advection. Now, positive omega means sinking air at 700 level. At the 850 level, cold air advection. At the above 500 level, negative vorticity advection. Significant upward motion occurs if we have super negative omegas, which are 3 millibar per second. All right, we have two inversions that you need to know. Subsidence inversion is if we have warming above. That's the inversion that you might usually know. But you could also have radiation inversion when there's cooling below. So warming above, cooling below is what radiation is. I'm going to get like carpal tunnel trying to type this way because it's not a very good thing, right? Short waves are found better. I should really have said, are they more easily identified at the 500 millibar level or the 700 millibar level? More at the 700 millibar level. 850 millibar level, going down one more. What millibar, keep saying that. Meter, it's at about 1500. What things can you see here? Thermal advection, which is the CAA, the WAA. You can also see fronts here in the low-level jet. Will the front slope up or down to colder air? Up. Warm air advection means upward or downward motion. Upward. Atmospheric expansion or compression, not decompression. Compression. Expansion. Cold air advection means downward motion and compression. Cause of thermal advection. Why the hell does this occur? Because isotherms are starting to intersect with the height lines because we have different flow here. The low level jet is an area with increased wind speed, just like any other jet. What are the three causes? Okay, of course they're already here. But or associations. It's associated with the warm sector of a mid-latitude cyclone, which is the area in between the cold front and warm front. It's associated with the exit region of the upper level jet that's above. Talking about jet stream, by the way. And Rocky Mountain nocturnal healing or cooling. Sorry, I there's a song I like called Rocky Mountain Healing, and that's by Ray LaMontagne, and I got mixed up. Sorry. That's what happens when you do a stupid video like this late. I shouldn't say stupid. Okay, it's not stupid, but um, kind of long to do. Um, ugh, back on track. Isobars tilt up or down towards the mountain of the nocturne down. They're like tilted down right by the mountain. All right, move. Okay. Now, surface stuff. METAR stands for what? Meteorological Terminal Air Report. ASOS and AWOS are components of METAR. ASOS is Automated Surface Observing Systems, made possible by the National Weather Service, FAA. Over 900 stations. Really important thing is that it's at 1 hour intervals. AWOS is the older thing, reports every 20 minutes. So even though it's older, it reports quicker or like at more intervals. All right. For a surface air plot, what are the different things? All right. Number one up here is temperature in Fahrenheit. This is dew point in Fahrenheit. Actually, there's something missing. The symbol that's right here is the weather that there is. Dots mean rain. Asterisks mean snow. Um, there's other symbols that if you want to review, please go back to the video, but it's pretty straightforward, honestly. The circle tells you cloud cover. So in this case, this would mean clear, and it's an octa. So the more covered that is, the more black it is, the more cloud cover we have. Completely black would be overcast. Wind barbs, is what this is, and uh, if you have a half barb, which is just a line, it's 5 knots. Full barb is 10 knots. Flag, which looks like the triangle, is 50 knots. 50. 1 knot means 1.15 miles per hour. How do you decode the pressure, which is what this 3 is? The pressure, you need to add a 9 or 10 to front and decimal. So let's say we had, I'll just have an example, okay? Let's say it said 107. That means you would first add a decimal here, so 10.7. Now you need to add a 9 or 10 to the front. So you first add a decimal in between the last and second to last number. Then 9 or 10 here. So does that make sense? No. That doesn't, if our average pressure is 1013, 910 is super low. That would only mean like a tropical storm or something. That's not common. So it would actually be 1010. Now, if we had something like this, let's say 888 or something, then you do 8, and then that makes more sense, 988.8, which is still, that's actually pretty low, but that's still what it would be. If that was the case, because it wouldn't be 1088, that would be too hot pressure. All right, order of flight rule colors. So we will have colorful uh plots that can be 4 different colors, and the color tells you how good the visibility is. And the order that you can remember is GBRM. For me, I remember that a weird story. I had a substitute a few times when I was at this school, when I was in 8th grade, and her name was Miss GB. And anytime that I had her as a substitute, she would I don't know if she was like into, don't know if you would really say witchcraft. Like, I don't mean that like in a negative way, like that, but I don't know if that's what it really was or not. But it was a kind of interesting thing because she would always ha be stirring some like strange stuff that would have some aromas in the room. And so that I just remember GBRM. Miss GB would make the room RM. I don't know. That wouldn't mean anything to you, but that's the colors: green, blue, red, magenta. Magenta worst flight rules, worst visibility, green best visibility. All right, now other miscellaneous things. Zonal flow, I already said that's east to west flow. Meridional flow, north south. Meridians run from north south. That might help you remember that. How do you know which way a trough will move? A trough is going to move. You just look at the way that the jet stream looks. So let's say the jet stream looks like this. This is the trough. It's going to move at first kind of like north or east. That's I know my directions, obviously. That's kind of northeast, like eventually northeast, but really just east at first. And if it's like this, well then, that you just look at to what's exactly to the right of the trough to know. That's how you do it. Um, Trying to erase this thing. I always Zoom needs to do better about letting you erase things. It's just stupid sometimes. Okay. How or is in a relative vorticity map, greatest positive vorticity advection is going to be where? It's going to be um to the center or inside of a curve. Well, actually, it's really going to be to the right of the trough. I don't, whatever I was looking at, that's not right. It's going to be to the right of the trough because it's about the fastest things are about to go there. Fastest, uh, the highest vorticity is about to be affected there. Sorry. The greatest shear is where? Um, the greatest shear is going to be. Oh, I was looking at the wrong thing. This is center or inside of the curve. That's why I said that wrong before, because I was looking at one below it. The a deep layer moisture exists at 5 dew point depression of 5. In the 700 millibar, um, the warm air cap comes from, we didn't really talk about that, but it comes from the southwest. The strongest warm air advection is at um, the top of a ridge on a surface map. Strongest cold air advection is at the top of a trough of a surface map. Um, what millibar level will could steer air mass thunderstorms? Remember, convective stuff, that's going to be at the 700 millibar level. The warm sector is in between um, here, I'll just draw it. In between the cold front and the warm front of a mid-latitude cyclone. So this is the warm air. So there's warm air advection here. There's cold air advection here. This is the low, the mid-latitude cyclone, right? What are the three ways to identify a front at the 850 millibar level? Well, you know that there's a front if you see a wind direction change, if you see a temperature change, or a moisture change. All right, now we're getting on to this good data stuff, okay? METAR, you got to read METAR. Now, for this exam that is going to follow what I'm doing, you only need to know how to read METAR and MBM. MOS, I know we learned that, but it's really being faded out and it's quite similar to MBM and somewhat irrelevant these days. So that's why we're not going to look at that. But we'll read these four and let's see if we can know what they are, okay? So let me just kind of stretch for a second because I'm getting a little bit tired. And let me have a little bit of some Coke. See? Okay. Just skip the video ahead. Okay. Or actually, I forgot. I can pause this. So let me pause this while I drink some Coke. Okay, I am some Coke has been thermally advected into my system and I can now read this METAR. Okay, let's start with the top one. All right. KSDB. That's the station. I don't know where the heck that is. You don't have to memorize that, but all right, now what? 28/1740Z. That means it's the 28th of what month? You don't really know because this is just an example, but um it's whatever month you're in. That should be obvious. 1740Z. Okay, that's the t Zulu time, and I'm in EST, so right now, since it's after daylight savings ended, um you do -5 hours. So 17 minus 5 is 12. So that meant that this was at 12:40 p.m. Auto means it's an auto station, automatic. That next thing, all right, 340, the wind's coming from 340 degrees. It is 19 knots. It's gusting up to 28 knots. Visibility, 3 statute miles. Haze is present. Overcast. Now, this you add 2 zeros. It's overcast at 100 meters. Temperature is 12 degrees. Dew point is 8 degrees. A That's the altimeter reading, which is 30.03 inches of mercury. Mercury. I don't know why. I always struggle to say that word for some reason. Um, all right. I don't I Without sounding like I'm like country. Um, further remarks. That means other, shit that it feels like telling you. Okay. All right, AO2, that means this thing isn't freaking stupid and it can determine temperature type or precipitation type. If it was AO1, it would be like, too bad, I don't know what type of precipitation it is. Peak wind was coming from 340 degrees. It was 28 knots and it happened at 1736 Zulu, which would have been 12:36 p.m. EST. Now, this thing is telling you the exact temperature and dew point because it's like, oh, that we just rounded it there. How about one more specific here? That means it is positive. This zero means positive, 12.2 degrees Celsius, positive 7.8 degrees Celsius for the dew point, and that's obviously rounds to what you see there. All right, that's the first one. Now let's read the second one. Okay. Ugh. All right. Station is the 29th of the month. It's 16:53 Zulu, which means 11:53 a.m. EST. Automatic station. Wind coming from 160 degrees. 12 I hope you can see my cursor, by the way. I really do. If not, this it won't be very good. Tw 11 knots winds gusting up to 23 knots. Um Oh, we have something different this time. So this is 130 V and then uh 190. So let's see here. This time, okay, I actually had to look up what that is. That was not something that I said, and I'm not a METAR expert, but that actually is telling you that the wind direction is varying from 130 to 190 degrees. Visibility is 10 statute miles, negative Ra, that means light rain, scattered clouds, scoot at 120, or sorry, 1,200 meters, um, and then overcast at 1,900 meters. Temperature 12 degrees Celsius, dew point, sorry, 11 degrees Celsius. Altimeter 29.96 inches HG. I'll just say HG. Additional remarks. The thing isn't stupid. It can detect temp or precipitation type. Peak wind. You know what? I just won't say that because I will skip the things that I already said. Slip sea level pressure. This time it feels like telling us that. That is what? UC144, you can be like, okay, it's 1014.4. Remember, you can add a 9 or a 10 to the beginning. P0004. What is that going to be? That's going to be the 1 hour precipitation in hundredths of inches, so only 400ths of an inch of rain. We already saw that before. All right. Look on this one. Let's see if there's anything new. Um, that means light snow. This time, this is negative temperatures, -4 degrees Celsius, -6 degrees Celsius. Um, oh, let's see here. There's some other things that we didn't talk about before, so don't have to worry about those. Um, uh, yep, that's pretty much the main things that you need to know for METAR. So let's move on. All right, MOS. Remember, MOS is modeled output statistics. So it's basically, let's take models, GFS or NAM, and let's apply statistics to them and then tell us some things. So the predictors are going to be the things that are gathered from the models, and the predictans is going to be what's displayed in the MOS data. What's some strengths of MOS? It helps to correct for model error. Weakness of MOS, if there's extreme weather, it is bad. So for extreme weather or unusual circumstances, it's bad. Also, um, not very public friendly. That's why we use NBM more now, because there's things in here that are not as easily publicly digestible. All right, we have MAV and MEX. MAV is your short range MOS, which is reported 4 times a day, and MEX is long range, and it's only reported 2 times a day. MET is just basically the text-based product that we get if you're running through NAM. Now NBM. All right. NBM is somewhat similar to MOS, but more updated and pretty much better. 31 systems total are used. It stands for National Blend of Models. And standard deviations, remember we have some things like TSD, DSD. We have standard deviations provided. This helps you to correct for model bias by showing you if there's some difference between the models. Because the higher the standard deviation, the less certainty there is. What does SWH mean? Significant wave height. That you don't really need to know that. Then there's 3 types of NBM. There's NBS, that's the most common, shorter range, that's provided in 3 hour intervals. NBH, which is hourly NBM. NBE, which is extended NBM. But NBS is most common, and it's what we have here. And let's read this. And I believe, yeah, this is what I had in that video that was really not the best example because of all these zeros. But I'll still define what each of these mean just for review. So, all right, let's look at the top. Hopefully you can see my mouse, but um, KRBW means the station. We can see above that MBS. It's MBS. Um, and then it's part of NBM. The date we can see December 10th, reported at 0 UTC. That's when this was ran. The date, these are the different dates that are in the future that it will help us see. The first time that we see is 6 hours ahead of when the model was ran. So we see 6 UTC, then 9, 12, 15, because it's at 3 hour intervals. Forecast hours, how many hours total since the model was ran, and it goes up to 72 for MBS. TXN is going to be our max and min for the day. And where you see the number doesn't mean that's when the max and min are. It's just saying in that time period. And it's from what was before. So this 28 is showing the minimum for before that 12Z time, and the 58 before that 0Z time, and etc. Um, X and D we did not talk about. TMP is the temperature that was reported at that time, or predicted at that time. Sorry, predicted at that time because it's future, it's forecast. Temperature standard deviation, dew point temperature, dew point standard deviation, sky cover percentage, sky standard deviation, wind direction, wind speed. Um, Wind direction, you add a zero to the number. Wind standard deviation, wind gust, gust standard deviation, 6 hour precipitation, um, and probability, or sorry, 6 hour precipitation amount, in hundreds of inches, and it's very low, very low. Then 12 hour, then the Q, is QPF, quantitative, okay, quantitative precipitation forecast. For some reason, my mind just went blank. Obviously, I know. But that is basically if you melted, um, what liquid precipitation would you have, basically? And sometimes it's not even applicable to say melting, but zero, as you can see for that. Um, duration that precipitation is expected, zeros. That's why this isn't really the best example, but it would be in hours. And this is in hundreds of inches. I should say the units. Uh, Temperature TO3 and TO6 is that's sorry, that's not temperature. That is probability of thunderstorms, which is zero. Um, for 3, 6, and 12. And then preserve, that is probability of freezing rain, probability of snow, um, probability of sleet or ice. SO6 is the 6 hour snow amount, and that's in tenths of inches. So for the rain, it's in hundredths, QPF, hundredths, snow, tenths. Snow level is the height above sea level where precipitation will still be snow. If it's zero, it's occurring at the surface. If not, it's not occurring at the surface. IO6 is the 6 hour ice amount. CIG is the ceiling height, which means the lowest level where there's high cloud cover. -88, that really means it's unlimited, so there's not even that, so it's clear. IFC represents the probability of uh, needing the instrument flight rules. Um, so the higher the number, the worse visibility there is. LCB, the low cloud base, basically is the lowest place where the clouds are. -88 means it's unlimited. But otherwise, you need to add two zeros to the numbers. This is 16,000, this is 24,000, 13,000, etc. Visibility, that is in um tenths of a mile. So that means that you, in this case, that would be 10 miles. That's what 100 means, and that's the default. IVF, IFV, sorry, is the probability of a visibility that's less than 3 miles. MHT is the mixing height. It's where the top of the PBL is. And remember that PBL is the area in which we still have friction and play. We'd have AG strophic flow. Um, TWD is the transport wind direction, um, how winds are changing with height. TWS is the speed of that. HID is the Haynes index, which is basically almost the probability of wildfires. COSOL, sorry, is solar radiation. I don't know if you've noticed, I tend to sometimes mix up some letters for some reason, but I'm not an idiot. I promise. All right, we're almost done with this thing. Um, Hydrostatic balance, what does that mean? Okay, so this is just extra stuff, so kind of just random. Hydrostatic balance is if the pressure gradient force and gravity balance, not the Coriolis. That's geostrophic balance. The PBL, I actually recently just said that. It's the area close to the surface where friction is an effect. You need to take that into account. For the ridge, at a ridge, there are faster winds, um, because the centrifugal force is with the pressure gradient force, not opposing it. But for the trough, it is opposing it because it always points to the outside of the curve. Uh, for EST, how many hours do you subtract March to November? -4. But right now we're November to March, so -5. SKUT identification. So when you're looking at the SKUT log P, the horizontal solid lines are pressure. Um, from going from the bottom left to the top right, solid lines, that is your temperature. So this pressure increases logarithmically. That's why you can see that there's not equal distance between those horizontal lines as you go up. Temperature is tilted. That's why it's skew T. Um, Bottom left to top right dashed lines is your saturation mixing ratio. And that is the grams of water needed to saturate dry air. The top left to bottom right solid lines is your dry adiabat. Remember that is basically showing you what your DALR is. What will the part, this is what the parcel will do if it is unsaturated. Now, the dashed lines from the top left to the bottom right is your wet adiabat, and that shows you your WALR, and that's what the parcel will do if it's saturated. Now, remember, this is what this is saying. Um, these lines that we just described, they only are showing you where the whole numbers are, or like the zero numbers, like the tens, basically, whatever you would say, or fives in some cases. But of course, in between that, there's also the unrounded numbers. So when you're doing the parcel trace, you go parallel to that. It's not going to always be on the line unless it was that exact value. I talk more about that in the other video if that doesn't make sense. What does the red line mean? That's um that is what the environmental lapse rate is, how the environment changes, how its temperature changes with height. The green line is the dew point, and so this is just the temperature. And the blue or black line that there might be, it would be the parcel trace. Um, if the environmental lapse rate is to the left of the adiabats, which means that the rates at which the adiabats, if the ELR is to the left, that means that it's the rate is higher. The ELR is higher than the WALR or DALR. If that's the case, then that means that it's slower for the parcel to cool, and then it's going to rise because it's warmer than its surroundings, which means unstable. If the ELR is to the right of the adiabats, that means that that rate is slower. So that means the parcel is going to be faster than the environment to cool, and therefore it will sink, and that's stable. So remember, that's one of those counterintuitive things you got to be careful about. Think about it the right way. Where you switch from the DLAR to the Waller is known as the LCL because that's where saturation occurs. Where the parcel gets warmer than the red line is the LFC, which is the beginning of the cape and the end of the sin. And then the EL is the end of the cape. oh, this is just something kind of random to look at. Here there's positive vorticity advection because this strong vorticity is about to go there. This is negative because it just was there. This is neutral because it's just neutral. And then where we have positive omega, there's sinking air, cold air advection below, negative vorticity advection below, above. Negative omega, rising air, warm air advection below, positive vorticity advection above. And that's it. That goes over everything that was in this weather analysis one. And so I hope you do well on any exam you might have. And stay tuned for weather analysis 2 that will take into effect in about a month. Thank you for watching these videos, and I hope they've been helpful. See you later.